Yeah, thanks, y'all. So it's my yes, there are no colors on the slide, but on our screen it's very nice.
Microsoft is with a big S. The wrong seminar.
Immediately switching the slide. Thank you, Chris. You should provide a logo so that no one can misspell the name.
On the website.
Like how the KDVI is misspelled. This is the official logo provided by the university, and the KDVI is misspelled, so you know this is not really my doing. Yeah, so I wanted to give an introductory lecture, and I'm not really sure I will speak about any recent results, but I get the idea that this is not a usual topic for this Krystal seminar, so it'll be very introductory and example. All right, so to introduce you to who I am, my name is Krystal. I'm at the KDVI. I've been here 4 years. No, I don't speak fluent Dutch, if that was your next question. And this is the sort of research that I do. I work in algebraic graph theory, which we will look at a little bit what that means in the next slide. And it has many connections. It's an area of discrete math. It's related with graph theory, because if you remove this algebraic out of it, you would get graph theory. And we use tools from linear algebra, such as matrix algebras and association schemes, which also have connections to coding theory and other topics. But of course, there are many applications that I've worked on. There are applications in optimization and in this quantum walks topic that I'm going to talk about, which is the highlighted thing. So maybe a goal of this talk is to sort of explain to you how this topic has evolved in math and the mathematical tools we developed to study this problem that originated in quantum computing. And that maybe if you have a similar thing in your research and you would like a combinatorialist, this is the sort of thing that could be done. Okay, so what is algebraic graph theory, or maybe linear algebraic graph theory? The idea is that we have some object like a graph, which has some vertices, which all have names, which are colors. And we record all the information about its adjacencies in what we call the adjacency matrix. So this is the matrix whose rows and columns are indexed by the vertices of the graph, such that if you, is my cursor, is that? Okay. Yeah. It's actually Yop's cursor that, yeah, he's gaslighting me with. That, for example, the red and black vertices, they're adjacent, and there's a corresponding 1 in this adjacency matrix. And the black vertex is hopefully not adjacent to this bright green vertex, right? They're not? Great. Which corresponds to the 0 entry in this matrix. So you can store the combinatorial information about your discrete object in some matrix in this way. It doesn't need to be the adjacency matrix, because instead of looking at this graph just as a graph, we could draw it in the plane like this and consider it as having faces, these regions which are bounded by edges. And then you can write a different matrix, which is still indexed by the vertices of the graph. And the number that I'm putting here is the number of faces that contain both vertices. So I did make this slide in a hurry, so it could be that this highlighted entry is wrong. But anyway, this entry, it should be the number of faces containing both vertices. So in this case, it's the red and orange vertex, and I think I'm right. That only the yellow face contains the red and orange vertex. So the entry is 1. For example, the red and black vertices, correct? Not correct. Okay, yeah.
Well, there's
okay.
hidden face behind the thing.
Yeah, so the outside is also a face. The faces are these like red, green, blue, purple, yellow face, and then also the outside face. So for example, this red and black the red and black vertices, they're on the blue face, which is one face, and then they're also on this outside
But
face.
that, you can also see because of the diagonal is always 3, right? So the black is on 3 because there's 1 in the back.
Correct. So every vertex is on 3 faces by itself. So if you consider it to be a pair that's the vertex in itself, then they would be on 3 faces together. So this is not the adjacency matrix, but some other combinatorial matrix that you define using some graph objects.
Does it have a name?
What?
Does it have a name?
No. Yes, John.
Only define the planar graphs?
You can define it for embedding on any surface. So any graph has an embedding on some surface with some number of handles. That's many. And you can always, and what it means is it's embedded and there's some number of faces. So you can always discuss this.
So here's on a sphere, it's like embedded.
So this is like on a sphere. Sphere is equivalent to the plane by a stereographic projection. But you would think of surface as like I don't have a coffee cup, but like your coffee mug would have a handle. And you would embed more things.
And if you have a different embedding, I guess it can be different.
Yes, if you have a different embedding, it could have a different matrix and it could even have different eigenvalues and different things. Okay.
The square of the incidence bipartite graph.
Yeah, so it would be like NN transpose if you took the incidence graph of vertex face incidences, which is how this thing comes about. Vincent recognizes it. Did this thing have a name?
I don't know. Well, there's one thing also, because this is like a circular embedding, but it could be that a vertex appears like on a face in
Twice.
some sense twice, like if you
Yeah.
walk around the sides of the face. And then I
And
think
then you
our
have a
matrix-
decision.
Yeah, you have to count.
For
how
us,
many
we
more
would
faces.
have it appearing on that face twice.
But in this case, it's the same.
But we've chosen to have a non-problematic graph with none of these special cases.
How does a vertex appear twice?
If you walk along the boundary of a face, it can be traversed twice. This is maybe not so intuitive, but if you consider even,
In the plane?
yeah, it can happen in the plane.
Take it.
That you have this, and then you have some stuff. This vertex and the outside face, it will be visited twice. So anytime you have a cut vertex, it will be visited twice on the facial boundary walk. So we would say that it's on the thing with multiplicity 2. Yeah. If you, in the plane, if you assume that it's more than 2 connected,
And
then
I
it
guess
will
it
not
would be
occur.
even higher if you have more different like things dangling off of it, because you kind of keep coming back to that.
Yes.
same,
Yes, it can be even more. If you put more baubles, then it just gets visited every time. Yes, it can be even more, but every edge is only on 2 faces. So there are some limits to how often you can be visiting your vertex. You will eventually run out of edges with which to go to it. Yeah, excellent. So yeah, I see that you guys all like these matrices. Great. So the main idea of this field is that you use a combination of combinatorics and linear algebra to find the eigenvalues and eigenvectors of whatever matrix is relevant to your problem. And you use this to bound graph parameters like chromatic number. And a very typical question in the field is, suppose I don't give you the graph. I just tell you its eigenvalues. Can you tell me what graph it was? And this is a problem that is an open problem in the area that as n goes to infinity, the proportion of graphs where you should just know which graph it is, it should go to 1. So almost all graphs will not have another graph with the same eigenvalues. That is true for this cube thing and also some special families of graphs, but also for apparently almost all graphs. Some other projects we've done, I've done in the past is you define also not exact, yeah, the adjacency matrix, and you take some other function of its eigenvalues, and you would have two graphs, G and H. And then these eigenvalues, they have to satisfy some relation, otherwise there can be no homomorphism between G and H. So it is a very loose condition, but this is the type of a thing that can happen. So now, like sort of the result is not for the graph itself, but for all graphs that share those spectral information. Okay, so this is, yes.
You just said earlier it would almost solve the graph isomorphism.
Correct. Yeah, in fact, there are like many attempts to solve the graph isomorphism problem in sort of this manner. And it's like a very old result from the 80s that if 2 graphs, their eigenvalues all have bounded multiplicity, then graph isomorphism is polynomial time on this class of graphs. So for most graphs, it will be true, and this has been shown recently by Terry Tao and Vu, that almost all graphs have all simple eigenvalues. Their eigenvalues are all different, which is sort of what you would expect. It's very hard to have a repeated eigenvalue if you're just randomly generating matrices. And then, yeah, for this class of graphs, the eigenvalue multiplicity is bounded by 1. So then graph isomorphism is polynomial time. If you have 2 graphs, and this is true, then you can solve this problem efficiently. And also there are some classes of graphs which, before this landmark result of Babai, that is graph isomorphism, is quasi-polynomial time. There's a class of strongly regular graphs where everything that has the same parameters, there's some numbers that you define with a graph, and if you have the same numbers and you also have the same eigenvalues. And it was the graph isomorphism routine for this class was also faster. And it somehow used the fact that these things were co-spectral, and then it did some stuff. Okay, yes.
But just before you said that, for these large graphs, almost all graphs, they have this property. If you have the same spectrum, then they are the same graph.
Yeah, they're isomorphic.
Yes, but then you said something a bit more implicit. You said there is a polynomial time algorithm that distinguishes them. Like,
Yes.
but isn't that algorithm just diagonalizing the matrix, or
No,
is
it's
something
not.
is something faster than that? Like, or because I mean, you
Oh, no, but you don't know that, right? Like if I just give you a graph,
right? So you have to
unless
first
it's
find
a special graph like this graph,
yes.
it would be hard for you to prove that there's no other graph with these eigenvalues. That's like almost impossible.
You first
So
find the spectrum.
You have to be promised that there is no other graph with this spectrum, and then your routine would work. But the routine that I'm talking about is I give you the graph and I don't promise you that there is no other graph with these eigenvalues. In fact, I give you two graphs, they have the same eigenvalues,
Right.
but all the eigenvalues have multiplicity 1.
Yes.
And now we only use polynomial time stuff to determine if they're isomorphic. So this is exactly the situation where that doesn't happen. Like if you consider like a heuristic for graph isomorphism, you get your graphs, you compute the eigenvalues. If they're already not the same, there's no way these things are isomorphic, you just return no. But now we're always in this case, they are co-spectral. And it takes n cubed operations to n cube time to find this. So yeah, it's already not in the situation where they're determined by their spectrum.
But you're saying that if you would find that their spectrums are the same, and also that.
And also multiplicity 1, then there is an algorithm that tells you whether or not they're the same.
But it's not
there's an
automatic that
algorithm, or
they're
you could just say they must. be
No,
the same.
no, they don't,
Okay.
no. They can be isomorphic, but not, non-isomorphic, but have the same simple eigenvalues Yes.
Okay.
Like a nice canonical example of a pair of such graphs.
that have simple eigenvalues and,
Or like very, very terrible, like where the.
they're kind of like a bit terrible. I don't know. I think there's like a very simple example where if you allow disconnected graphs, I think you have like some path that has maybe, it's like this. And then maybe only 3 vertices over here. And this has simple eigenvalues and it has the same eigenvalues as the long version.
Like,
So-
okay, look at this.
Okay, whatever, the length of the paths are not correct, but there's some like little thing where you have 2 paths and then a path also with an isolated vertex and all the eigenvalues are different, but they are not isomorphic and they are co-spectral. It might be later in the slides. I think it does come up in the slides, so maybe when we see it, I will stop and point it out. Okay, but you can easily come up with such examples. You can also search on the computer and quickly find such examples.
If you look online, there is a example of it actually. So so just look it up. I guess it's
Yeah, so there's many small examples. Okay, great, fantastic. Let's move on to the stuff. Okay, quantum stuff. So loosely speaking, perfect state transfer is the ability to move quantum state from one location to another with no loss in fidelity by exploiting some Hamiltonian, some time evolution Hamiltonian instead of using swap gates. And the motivation for this, I have just copied from Alistair Kay's paper, that suppose you have a quantum computer and you have computed something, you would like to move the state to somewhere else, which is where you want to execute the rest of your routine, say. And you could do this with a sequence of swap gates. But maybe this would be prone to control errors and you want to somehow instead use a time evolution Hamiltonian to move the state over to take advantage of some structure of the circuit. All right, so they do this.
So you have, like, you imagine your graph is like physical, like spatial,
Yes.
and you have a state on, like, sort of certain.
So no, we don't imagine the graph as spatial, but the locations in the Hamiltonian where you put certain gates somehow defines a graph, which we will make clear. later.
Where are you transferring, you're transferring the state from somewhere to somewhere else?
Yes.
And what does that space come in?
What?
Like, yeah, what,
I think what's not clear, what is the overall space? Or is it like a subsystem?
Like
You know,
3 to the 2 to
Like
the
for one
n?
qubit, for another qubit?
Yeah,
So every vertex is a qubit?
yes.
I mean, is it an example if you have like a chain, a line, and you want to transfer a one qubit state from one end to another, and then you
Yes.
perform a bunch of swap gates, and then
Yes.
the line is just tells you, okay, you can perform gates between these neighbors, but not between others.
Yeah, but so that's the alternative. That's this, the alternative
Yeah, I
version.
understand,
But it will be like e to the ith, and h is some Hamiltonian, and it
Mhm.
implicitly defines a graph.
Okay,
So
and
I don't know if
you
it
will
needs
you will
to-
tell how it defines.
I'll tell you how you define the graph. This is like the fluffy slide of words before
Yeah,
there's
sure.
a slide of math. Yeah. All right, so this was defined in Bose in 2003. I got this wrong in my abstract, but I sent it to multiple people who did not correct me. I'm sorry. So it started as a problem in quantum computing, but it is now like a subtopic of algebraic graph theory, because many tools that, in order to work on this, you actually had to prove more things about algebraic graph theory so that you could apply them. You had to prove more things and also define things. And the things that were defined, like the notion of strongly cospectral vertices, they could have been defined without ever hearing of a quantum lock or a quantum computer or the complex numbers. But they were not, because there was no reason to study such a notion, but this provided the motivation, and now it is, many recent surveys in this, or maybe not many, but a few recent surveys in algebraic graph theory do include this as an application. Okay, so let us formalize our matrices. So the Pauli matrices are as follows. Hopefully none of them are wrong anymore. Oh my God.
Yeah, this is.
Okay, yeah, so ignore that one. We will not use that one. It's fine. The only two I care about were correct. Oh my God. Okay, so now you have this Pauli operator where I have an n-fold tensor product, and I have the sigma x in, or sigma y in the youth position. And the Hamiltonian, if you have if you're provided a graph, or if you're provided a Hamiltonian, you could now derive the graph. You would have these operators for every edge. So the edge is between u and v, and then you would have these pairs of operators as a part of the Hamiltonian. So this is where the graph is, because it's a sum over the edges.
so the point is that you're assuming that your system. So, okay, so you want to transfer a state from some qubits.
Some qubits.
I think it is what I meant by spatial, like you
Yeah.
have some qubits in this part of your lab and
Yes.
you want to transfer to some qubits.
But it doesn't have to be spatial. I mean, it can be it can be completely like also internal states. It can be spatially the same place, right? I mean, there is no notion of space. It's just how things are connected.
Okay, do you mean that like it could be that you're transferring to different degrees of freedom of the same?
Correct. Yeah.
Okay, I see, okay, I guess I think of it always as spatial, but okay. Yeah, I know, okay, but then, and then the Hamiltonian is,
And then you evolve it in time.
okay, and then this is like some Hamiltonian that you can implement for whatever reason.
Yes.
Okay.
Potentially. Okay, right, so yeah, that's the Hamiltonian, and then it evolves that if your state is, sorry, I don't have cats, is phi 0, then the stated time t is given by this. Okay, and there are other choices that you could have chosen to put for the interactions, and we have chosen this one because it corresponds very nicely. That the action of this H is equivalent to the action of the adjacency matrix. So a priori, this thing should live in a space that's C to the 2 to the n, but you can model it by an n by n matrix. Which brings us to an adjacency matrix of a graph. And now it's a,
Maybe the action, like, I don't have like a lot of intuition for like how it's written here, like, is H then the adjacency matrix?
no, H is this messed up matrix. H is the Hamiltonian.
And you don't get the adjacency matrix if you work that out.
You do not get the adjacency matrix. It's much bigger. It's 2 to the n by 2 to the n. But you can prove that the action is the same.
What do you mean by action? You mean it swaps qubit states in this way? Is that
Yeah.
what you mean? Okay.
Yeah, so like if
So it swaps a qubit state from U with a qubit state from V if U and V are connected by an edge and you acted with a Hamiltonian
Yeah.
directly on
Yeah,
this.
yeah, so this somehow corresponds exactly with the neighborhood operator of a graph, which is just the adjacency matrix.
Okay, so there's n qubits.
Yes.
So the dimension is 2 to the n.
Yes.
But then these states 1 up to n, do they represent like a 1
Yes,
In
a
the
one
first
in the first
qubit.
position and then,
and, okay,
so yeah, that 0.
and zeros
The
everywhere?
one, it would have corresponded for us mathematicians, it would have corresponded to this. And so on. And the other one would have been just a 1 in the first position.
So maybe Stacy, if you can rewrite this Hamiltonian like plus minus also. So it's equivalent to writing it as sigma plus sigma minus. So sigma plus just takes 0 to 1 and sigma minus 1 to 0. So then you can see how it just takes like if you have 1 in 1 qubit, it just transfers it down the chain to whatever you're connected to by just flipping this 1 by 1. That's how you can kind of think about it also.
I'm still a little bit confused what the notation cat 1 and 2 cat n is. Should I do this like the Hemingway 1 strings?
Yeah. Hemingway 1 strings inside the cats, and then these are Hemingway 1 strings, but in the vector.
Okay, I'll post
Okay,
it to
is that
screen.
better? Okay, good. Yes. It's a straightforward argument if you would have made these choices for the.
No, but I mean, yeah, because the Hamiltonian preserves a number that's up, right? So if you start with 1 up, you'll only have 1 up. You'll always stay in that manifold. So you'll stay in the Hemingway 1 states.
Yes.
And then all it does is just it takes the 1 to the next one, to the next one, to the next one.
The action of the adjacency matrix should be interpreted as a sequence of permutations.
It can be, yeah.
Wait, but I
Yeah.
guess it would actually take you, wouldn't it take you like H on 1, for example? If it's the adjacency matrix, it should take you to uniform
Yes,
superposition
of its
of all
neighbors.
the neighbors.
And but this is what this does also.
Yeah, okay.
So that's just all that it's saying. So now if you evolve it for some time, it's also the same action. Okay, so can we push this?
How much time? I think like a different amount of time.
Sorry?
Just need to infinity.
You get to choose the time. It is a time valued, sorry, it's a matrix valued function in time.
It's H does that, which is not unitary, right? Like,
Yeah.
it's not unitary to move from.
Correct. And then e to the ith will be unitary, and so is e to the ita.
If you think about it at very short time, you can think as the unitary being linear in age, right? For very tiny time step, roughly.
Right, so for us, for mathematicians, we're making the following simplification, that you have this u of t, which is the matrix valued function in time, where I just exponentiate the adjacency matrix, and it should maybe have been with negative t, but we're just gonna move backward in time. It's all very theoretical. So in particular, we care about the entries of this u of t, and it has perfect state transfer if there would be a time such that basically in the UvA entry, you have something that has norm 1. Okay, all right, so let us look at a non-example for our edification. So this is just a matrix, and this is the entry in the matrix. I can just plot this thing in time in the complex plane. Right, and I can evolve this for 100 amounts of time, and it looks like this. So this is C5 from the blue vertex to the from the blue vertex going to the red vertex, and this is the entry of this matrix. And if I look at it, I can already see that it will actually not reach the unit circle, so it will not have perfect state transfer between A and B. But I can also see that this is kind of interesting, and if I allow time to evolve more amounts of time, then I would get something that seems like there should be a theorem. And, and people have proven theorems about why this looks like this.
So you kind of got some shape, and these are like the sort of states, mixed states, something that you can cover with.
Yeah, yeah, the mixed states between these two vertices that are sort of covered. But presumably the mixed state should be the entire row of where you sent this vertex, and this is only one entry. But I can't plot in like n-dimensional space. Yeah, it's just the overlap of these two vertices. Okay, so this thing,
In this example, you're only considering these two vertices.
Yes.
But this unitary also.
do some stuff to the
probably
other
transfer to the
vertices.
other possible
Yes.
sites, right? You're
Yes.
ignoring that.
Yes, so these two things don't have perfect state transfer. I have not shown you or suggested that no other two vertices have it, but that is indeed also true. Yeah, so I mean, perfect state, it's for any, there exists some time, so I have not proven or even exhibited that there is no such time, but maybe this is so geometric that you're convinced that it will just stay inside this flower thing forever and never reach the unit circle. And these are things that you have to sort of, that are much easier once there are mathematical tools. So-
Achieve non-transfer because it has zeros. You can know for sure that nothing could transfer.
At time
Not
zero,
Zero.
at time zero, it has zero. Right, at time zero, 100% of your,
Right, right.
you're at
But then,
vertex
like,
A.
it seems like it comes back to zero. Like,
It comes arbitrarily close to zero because it's been there once and it's an almost periodic function. So it will come arbitrarily close again.
If you restrict yourself to two vertices, can you always use a spire graph to make the correct diagram?
No, this is actually a special thing that happens because the eigenvalues of C5, that they're quadratic integers. And you could do this if the eigenvalues of the graph would be quadratic integers.
It's a cycle.
It's a cycle, but the other cycles don't look so nice. So things do have a perfect state transfer.
What is the farthest it goes, it is from zero? So what is it?
What is the farthest? I don't know. It's like,
six.
I don't know, like
You know
0.7,
that rate.
I don't know, whatever that number is. But indeed, like, we should be able to know this, and that I think we don't know.
Something involves.
My bad. All right, unless we do know this, we don't know. It's fine. Okay, there are states, there are examples of perfect state transfer, and I see the animation didn't work. Oh, it did. Okay, from the red vertex to the blue vertex, if you think about making a path. But of course, these are the only paths with this. And this is an early result of Matthias and a whole bunch of people. And I'm not sure that I cited the right paper, but anyway, it's multiple papers from the.
If you're considering this is one graph.
Yeah.
And you can.
No, this is two different graphs. So this graph has it from the red to blue vertex, this other graph has it
Oh.
from the red to blue vertex.
But for any longer path, you don't.
Correct, you don't, I know. But you can always construct a hypercube of whatever dimension it is, and it does have it between the farthest antipodal vertices. So this is a two-dimensional cube, otherwise known as a square. It has it between these vertices. I couldn't bring myself to draw the cube on 16 vertices, but whatever, you can imagine what it is. It has it between the vertices that are farthest apart, every pair of vertices that are farthest apart. And they have this also in their paper because these are actually products of K2. And if the graph has it, then all of the iterated Cartesian products with itself will have it. And these are just products.
How does the required time scale with the dimension of the hierarchy?
I think it's just the same time all the time because it's the Cartesian product. So it's just pi over 2 all of the time. And in fact, when people started working on it, like the physicists asked us, like, are there other times other than pi over 2? Because that's the time that we found. And it was actually hard to find something that was arbitrarily close to 0. Yeah, you can make that occur. And one of the things we did, which is just a mathematical curiosity, is that if you allow me to perturb some pair of vertices, I can always force it to have perfect state transfer if the original graph was a strongly regular graph with some properties. So this is just an example of these things have very nice eigenvalues. And we will see that this perfect state transfer, because we've reduced it to this graph case, it is just some property of some eigenvalues that took a long time to identify what the properties should be. But once you do it, you can control them and you can just force this to occur. This is maybe difficult to implement, but yes, John?
What is a perturbation of graph?
Yeah, so it is allowing me to put some number of loops on the red vertex, the same number on the blue vertex, and mess with this edge in some way. So in the Hamiltonian, we would have to change the coupling strengths
Weighted graph.
But there has to be then an edge or like multiple edges allowed between the pair. for instance.
That's, yeah, so you have to be able to change the coupling strength of that pair in the original Hamiltonian.
So when beta lotness are integers here, yes or no? Because
No,
before,
no,
so your Hamiltonian has now also non-unit weights potential.
correct,
Okay.
yes.
So if you didn't want perfect state transfer, would
Yeah.
this be sort of obvious? Because couldn't you just put such a high weight edge between these two that basically the graph was essentially,
It just stays there? Yeah, but that's actually not what
but you get actually perfect, which is.
you can get actually perfect, and I think this alpha and beta is not so unreasonable.
But if you add this very high weight, then it's somehow almost perfect. Well, this is exactly perfect. Is that correct or no?
No, so if you put the arbitrarily high weight, then maybe at almost all times you're in some like very high combination of those two vertices, but you cannot force it to be one or the other. You can maybe not even force it to be close to being 100% at the other vertex.
This is like, if you put like, as the weight goes to infinity,
Yeah.
your graph approaches the line of length one that you said does have perfect state.
Yeah, just for a very small time.
Oh, okay, like you put a huge weight on those two vertices only, and there's nothing else in the graph.
Yeah.
Okay, then yes.
But then it still is only approaching perfect, but you're saying that your thing actually achieves perfect.
Yeah, it's exactly perfect. But these are examples. So it turns out that on the IBM quantum computer, you can implement a time evolution Hamiltonian. So let's go do that. Because I've taken the step to share my entire screen for this reason. Oh my God. What? Can you not make it bigger? This is the size of my screen though.
Yeah, no, but you can get.
You can double click in it.
Double click? Can
Yeah.
Can you double click?
Double click in the big screen.
Okay, y'all. Go on. That's not my mouse. That's his mouse now.
I'm just gonna make it
Oh,
worse.
this is the web browser.
Don't make it complicated or anything. Just let me run the stupid thing. And,
Fox?
F12.
Yeah,
No.
think a little fox shop.
oh my God, what are you doing?
There's
Okay.
Fs on this one. Oh, F12. Are you sure?
No.
No, I'm not.
Okay, look, here's the IBM quantum platform. I have run 52 seconds of stuff. Yeah, there are multiple failed jobs. I don't know why. Okay, so, and now let's just attempt to run a job on this thing. So the first step is to input the stupid quantum circuit. So it does exist it's not a native gate on the computer, but it does exist that you can make this Hamiltonian. And this is the thing, oh my God, what is happening? Okay, he double clicked. Okay, that you can implement this Hamiltonian, which corresponds to C4. So one of the examples that was on the previous slide, this is that thing. It has perfect state transfer at some time that I have hopefully correctly inputted, and I have drawn it eventually. Okay. And then the next thing to do is to connect with this Brisbane quantum computer and transpile the circuit. So it will take my circuit and output some other quantum circuit, which can be run on its hardware. Transpile, I don't know. I think it's like compile, but it's not compiling it, it's transpiling it. Okay, it's a function. I don't know. Okay, it has native gates that it can do. But of course, you should be allowed to put a swap gate on some qubits, but swap is not one of the native gates that it has. So it has to convert whatever you wrote into stuff that actually exists.
So does transpile mean that you sort of just take a circuit and you transform it to an equivalent circuit?
Yes, an equivalent circuit, but that works on their computer. So for example, like, I believe you cannot.
Some epsilon.
Yes. Yeah, so there's already, there's gonna be a lot of epsilon. I think this epsilon that you just said is not gonna be noticeable.
Because I'm sure the quantum computer doesn't make mistakes, but. Translation.
Okay. Right, so, yeah, so transpile, it just outputs another quantum circuit that could be, so for example, I think that, I don't know, qubits 1 and 5 on their thing, it can actually natively not put a 2-qubit gate there or something, but then of course you could do it. So that's what transpile means.
C4.
C4, so the 4 cycle, 4 qubits. Okay, so now we have made our thing. we have allowed
Did
it
you show the
to,
circuit or not, or is it not yet?
yeah, so if we show the circuit, it's very slow. I think it's this, right? And now the PDF is suffering. Thank you, Vincent.
Okay.
Is it doing something?
So you showed it before, right?
I did, no, but that was a different circuit. Okay,
Oh.
okay.
Oh.
Okay, it's loading. See, it was doing it. It was just doing it extremely slowly.
The transpiled circuit?
Yeah, this is the transpiled circuit. Oh yeah, it's just going. Yeah, it's 127 qubits, most of which are blank and some of which are doing this stuff.
Why is there so much empty? Are these all empty?
Yeah.
Qubits? They're not used, or-
Can't make it just.
No, I cannot.
Okay.
Perhaps other people can, but I was not able to. Okay, so the next step is now we have this transpile thing that we've kind of looked at, but not really. We can run it on the IBM quantum computer.
It's funny that it took a graph theorist to demonstrate a quantum computing people how to use a quantum computer. I
Yeah.
never had a demonstration.
So I did this thing. Where is the refresh button? Okay. I did run like a large number of jobs, as you can see, and most of the, oh my God, it completed it? What? 390? Is that
I'm
what?
so
we did?
surprised, Krystal.
Okay, one time I was in a 7-hour queue. So I've actually run this yesterday. And I was just gonna use that if, oh, okay, it is this job. Okay, great, fine. It did it. It took some number of seconds. We can actually, I can show you what it looks like. Where were we previously?
By the way,
Sorry?
you have to pay for this.
Of course I don't have to pay for this. Where did that?
Very expensive.
Yeah, so it was
Something-
1,000 per second after this 10 free minutes that I have.
Per second.
US dollars per second, I think.
Really?
Yes.
Wow,
Okay, so this is the thing.
that was a joke.
Yeah. Okay, and then it has the thing here. It also has printed the circuit for us in a non-stupid manner. Oh, look. And it is measuring the qubits at the end. Oh my God, amazing. No, go.
So what was the original graph? Was it this?
It was SQL.
Before, like,
It was this graph.
Oh, this one.
It's this graph. Okay, and then, okay, and now the last step is to look at the results. So we did it, it has executed it, the job whose name is job has done its business and it potentially has some data for us. So let us plot this. I actually forgot what a bar plot is from like high school, so I did need to ask ChatGPT what that was. But fantastic. Okay. This is the output.
That doesn't look like perfect state. I'm surprised.
It doesn't, but there is a huge bar, okay?
How do we?
Yeah.
Conditions for-
What? I have no idea how we read this, but I think that the box.
I think we want all the bar on the first one, I assume.
Correct.
Where do we start?
0?
I think that
No.
qubit 2
Okay.
is recorded last, because the last time I transpiled it, it also did this. That because I didn't output the measurement to specific classical bits that I made myself, it somehow permutes them in the machine.
Can I ask what state you transferred also?
So I think it's supposed to go from 0, 1, 0, 0 to 0, 0, 0.
Yeah,
1.
no, but because also like
I
mentioned-
transferred a sigma x. So I did a sigma x first. It starts in all zeros, and I did a sigma x first, and then I did this time on the first qubit. And then
So
I
you
did
mean,
the,
sorry, what is the base? So you started in this 0 plus 1 basically then.
yes, with a
Yeah,
single one, and I should move to another single one.
But it can't, no, but if you do a sigma x, I mean, that's my question is what's the basis, right? So did you start in up or did you start in an arbitrary state of up plus down? Because if you start in an up plus down, then if you have dephasing, this is much, much worse. But if you start in a state
Well,
that's
okay.
up,
So
it's
the
not
computer
relevant.
starts in all zero. It starts with
Yeah,
every
but
every
no, I know,
qubit.
but if you can prepare, so my point is that if you have certain errors in your computer, such as dephasing, then
Yes.
it's much harder to transfer the state because you have to preserve phase information. But if your state is just 1, then it's a easier state to transfer because you know there is no phase information between components. So my
So
question was
there is no state. It is just a sigma x. Like
Just-
this is what I did. It should
yeah,
start
so
at all
sigma x
zeros.
and the
I
base,
did
and
just
so you
one.
start in 1 basically.
Yeah.
Okay, fine.
Yeah.
So not
And just because we have this slide where I somehow implied that this would be different from doing swaps to move the gates, I in fact did that. You can also move the state here to qubit number 2 in this manner. And this was the output, which is also not perfect, but it's better. Okay.
There's the path, right?
Yeah, but I also only moved it 3 qubits. Like, cause there are 4 qubits, but I actually only moved it distance 2. So then I did this, which is analogous.
Why are the x-axis not sorted somehow? Like what order?
Yeah. Okay. Well,
That's probably IBM's.
yeah. No, that's what I did in the thing. I just allow the things to, I just look at the results and I add them to the dictionary and I increment the count every time I see it. And I didn't sort the keys. If you want us to sort it, we can sort it.
No.
We cannot actually not sort it because this job is not active anymore, but
Can we see
the other one we
big
can
bar
sort.
plot?
Sorry,
You see the big bar plot again?
the other one, this one? Okay, I can sort it.
You wanted
How many
you wanted to transform 1, 0, 0, 0? Is that the initial state?
Yeah, so,
Where is that? 1, 0, 0?
Of course, 0,
Why is
1,
it so
0.
weird?
No, you just only. No, you only sorted the keys, I think. yeah.
I only
Not
sorted the
values.
keys? Oh, Okay.
Not the bars, that's okay.
Oh, now also.
Oh, I didn't,
You must,
I see, okay. Yeah, I didn't sort the values accordingly.
yeah.
Okay. I see the issue.
Sort by.
Okay. All right, I'm not gonna fix this in, even with Copilot live, but whatever. This is sort of, yeah, so maybe the key thing is this is execute, oh, yeah, we use all the time, this is great. Yeah, you can do things on the quantum computer. It's actually not very hard. It does produce some, imperfections, shall we say? But yeah, at least it ran it instantaneously and only took 3 seconds. So yeah, is it worth $3,000? Okay. Right, okay, so maybe in the rest of the time, I can give you an idea of the mathematics that went into perfect state transfer in the next 5 minutes, and then we have lunch. Okay? All right, so what we wanted was to, like, once you reduce it to a problem that is about the adjacency matrix of a graph, what I would like as an algebraic graph theorist is that it is a property that only uses the eigenvalue. So if I compute the eigenvectors, I can find out whether or not there is PSD. I don't want to search an infinite number of times. So to determine if it occurs, and I would like to predict it. So, and this is I feel like this is nice because it's like a typical story of how math develops, that when you have a thing and you don't know what the theorem should be, then we just look for this behavior in special families of graphs and hope that it generalizes. And this is a situation where that worked. So people study just perfect state transfer in paths, and then in just hypercubes and just very special Cayley graphs of Z2 to the n. For example, small generalizations of previous things. And there is like a pattern of what the characterizations of perfect state transfer involves. So you restrict yourself to a very small class of graphs so that your mathematics becomes easier. And then you say that the graph, which we're denoting X, it has some perfect state transfer between some pair of vertices, if those vertices are very special to each other, and also the eigenvalues satisfy conditions. So now what do we have to do? We have to say, what does it mean to be very special, and what are these conditions? So even in the very first theorem that they have, which is apparently this one with 2005. No, this is not the first paper. This is some later paper. But what they showed is that if you have a graph admitting a mirror symmetry, which I think they just mean reflecting across some axis, like the path graph, then the ratios of certain differences of eigenvalues must be rational. So this sort of fits into this framework because this mirror symmetry is taking care of the vertices being special to each other. They're exactly the ones that are reflected to each other. And then what it's also showing is that if you would have to have PSD, then these are the eigenvalue conditions. So this is sort of, there are many results of this type. And basically in 2010 or something, Simone Severini was a postdoc at University of Waterloo, and he brought this problem to the combinatorics and optimization department. And my postdoc and master supervisor, Christandl, the author of algebraic graph theory, decided that it would be a problem in algebraic graph theory and proceeded to make it so. And then they did this in various Cayley graphs where they again came across this recipe. And over 3 papers, Basic characterize this for Cayley graphs of cyclic groups. So there were some difficulties, but basically from looking at it in special families, people were eventually able to say what it means for those two vertices to be able to have perfect state transfer. And so now what we have is that if you have the adjacency matrix or any Hermitian matrix or symmetric matrix, then you can write the spectral decomposition, which is you can write it as a sum of projections that are weighted by its distinct eigenvalues. So these theta r's are the distinct eigenvalues of the matrix A, and this ER is a projection onto the theta r eigenspace. It's not subspace, it should be eigenspace. So if I take any vector, and if I do ER times this vector, that will be an eigenvector for theta r. Okay, so a concept that existed for a very long time in spectral graph theory is how are two vertices similar to each other? And one of the ways it could be similar is it could be cospectral, which is that if I look at all of these idempotents, I just look at the diagonal entry that corresponds to those vertices. And if this diagonal entry would be the same for all the idempotents, the vertices will be cospectral. And the thing that we want is strongly cospectral. So it's a strengthening of this. Not only do we need those diagonal entries to be the same, we actually want the whole column to basically be the same up to a sign change. So two vertices are strongly cospectral if you look at every spectral idempotent and the corresponding columns are identical or -1 of each other. Okay, and
sort of like understand this thinking about the graph.
yeah, so thinking about the graph is a little bit difficult, but we have a page of examples and non-examples. And what Chris showed, even before he defined this thing, is that if you have PSD between U and V, then those two vertices have to be strongly cospectral. So in particular, they have to be cospectral, and then in addition, this business has to hold. So mathematically, being cospectral is just an algebraic relaxation of living in the same orbit under the automorphism group. It's like the natural next step. That if there's an automorphism that takes U to V, then they will be cospectral. And in fact, if you delete it from the graph, delete either of these vertices, you get the isomorphic graphs. These will already be cospectral. And then the definition of cospectral originally is that you delete the vertices from the graph, and the remaining graphs are not isomorphic, but they have the same eigenvalues. Then I say that those vertices were cospectral. And that's sort of how it is an algebraic relaxation. So strongly cospectral is much more difficult if we think about combinatorially in a graph.
What happens with vertex transitive graphs?
It depends. Vertex transitive graphs, every pair of vertices are cospectral.
Right.
Yes.
That doesn't make sense to me.
What do you mean?
I don't know.
They're not strongly cospectral. So this complete graph is a vertex transitive graph. Every pair of vertices is cospectral, and no pair of vertices is strongly cospectral. And you can also have the star graph. You have K1n. I think these vertices down here, they're all pretty similar to each other. And indeed, every pair is cospectral, and no pair is strongly cospectral.
So this is making strongly cospectral seem like a ridiculous definition, because like how are they like,
But lots of
examples of like they're the same vertex somehow.
Yes. Yes. So it has to be stronger than being the same vertex. And you have your vertex transitive graph. Yeah. They have to be also like similar in a special way. They have to be similar via an involution. And also that the eigenvalues have to still align. So every pair is cospectral, no pair is strongly cospectral.
How does this connect back to the Cayley graphs on 2 to the n cyclic groups?
Yeah, so Cayley graphs are on Z2 to the n. In the hypercube, you have the case where you do have pairs of strongly cospectral vertices. And this is how they manage to characterize it. If you have a Cayley graph over certain things, and you have a vertex in it, it's actually not possible for there to exist a strongly cospectral vertex to the one you already chose. So then you can't have perfect state transfer in such a graph. So this is how they were eliminating it. And yeah, and maybe the poignant thing, so in the path, these pairs of vertices are all strongly cospectral. And a theorem that you can prove is that if you are strongly cospectral, then every automorphism that fixes one of them also has to fix the other one. So not only do they have to be the same, as in under the same orbit, under the action of the automorphism group, they need to induce the same stabilizer group, not isomorphic stabilizer groups, but equal stabilizer groups. So it's a stronger, like things could be the same, but they could be like more the same. So yeah, it's a strengthening of this thing.
So every vertex has a unique partner, is that it, or?
Yeah, so every vertex will have a unique partner for PST, but you could have sets of vertices that are all mutually strongly cospectral of arbitrary size.
Oh, okay, that's possible.
Yeah, 3, 4, 5. Yes, it was very weird when we found the first example that has 3 pairwise cospectral things, but whatever. It's actually very easy to construct 2 to the n things that are all pairwise cospectral, but the odd numbers are hard. So John, your example is about to come. In this graph, these 2 vertices are cospectral, and this graph happens to have simple eigenvalues, and these things are also strongly cospectral. So if you delete the blue vertex, that graph is cospectral to if you delete the red vertex, and they are not isomorphic but are cospectral. Okay.
That's the picture you were trying to draw.
Yeah, that's the picture I was trying to incorrectly draw. Let's cover it with the other board quickly. Look at the correct picture. Okay, so the smallest matrix algebra, the other way that you can force this to occur is that you can look at matrix algebras that contain the adjacency matrix. And then if it would have a basis of this matrix algebra that is an involution permutation matrix, then there would be strongly cospectral vertices under some conditions. Okay, so yeah, I see the food arriving, so I'm eager to finish. But at the time, in 2011, it was kind of hard to imagine what the statement should look like. Even when we proved this theorem, it was really not clear what the characterization of perfect state transfer should be. What you really want is that you're given a graph, and then the theorem outputs it has it or it doesn't have it, and if it does have it, at what time it should be. And yeah, this is the final thing that came out of Gabriel's thesis, and it was actually in 3 papers in the same year. Yeah, you can have a characterization. It's if and only if the vertices need to be strongly cospectral, and then that's Yop doing stuff. And then also the eigenvalues basically almost have to be integers in satisfying some condition. That's a generalization of what was in Matthias's paper. And then in this case, you can compute whatever this little delta is, and the time of PST will be an odd integer multiple of whatever this is. Okay, so great. How many slides are left? Yeah, so there's a mathematical extension that you can easily make called pretty good state transfer, which is that for every epsilon greater than 0, you can come within epsilon of having transferred the state perfectly. And they still have to be strongly cospectral. And yeah, I think the really cute theorem here is that the path, it doesn't have perfect state transfer if it's not P2 or P3, but it would have pretty good state transfer when it is 1 less than a prime, twice a prime, or a power of 2. It's very number theoretic. And when they did this, like these ideas were very new at the time, and they kind of forgot that it would not be the same for all vertices of the path. So their theorem is only for the endpoints of the path. But you could have internal perfect state transfer, and the complete picture is this also number theoretic fact that n+1 is 2 to the r times p for some prime. So I don't know what is happening, but there is some prime number business happening, which is very cute. And yeah, okay, so let's skip this whole thing and come to the thing that if you need eigenvalues / eigenvectors of a matrix, and the matrix is indexed by combinatorial objects, then I would like to hear about it. And let's stop and go to lunch.